Okay, this problem is 1332 out of the textbook. Chapter 13, Chemical Kinetics. That's a reasonably straightforward, simple problem. Dealing with chemical kinetics, you'll see this in your first online homework assignment, this type of problem. We're supposed to consider a chemical reaction. Here it's the decomposition of NO2 into nitric oxide and oxygen. And we want to know what is the average reaction rate between 10 to 20 seconds, and then also 50 to 60 seconds. So there's two different time intervals that we want to determine the average rate over, and what is the rate of formation of oxygen between the latter time period, 50 to 60 seconds. In the problem, we're given data that looks like this, the data table, which basically gives us the time and the concentration of our reactant that's undergoing the decomposition process at each time. It starts at 1 molar concentration, and at time periods after that it drops because this reaction is taking place and we're using some of this up, and as a result the molarity or the concentration of our reactant is dropping over time. Now, of course, our job is to assess the reaction rate, specifically the average reaction rate, because remember, there are different reaction rates that we need to consider. There's the average rate over some time interval, delta t, and there's the instantaneous rate. And those things are going to be different, okay? So you might see problems with instantaneous rate. This is the average rate over some time interval from tabular data. So let's just kind of jump into this and sort of see what we can come up with, okay? So the average rate over some time interval can be described as the change in concentration per change in time. Change in concentration of some reactant over the change in time, okay? What I'm going to do, sort of update that equation a little bit, and instead of writing changing concentration, I'm going to expand that to final concentration minus the initial, because if you think about how much the concentration changes, this really defines that for us. Final minus the final condition minus the initial condition. Now, if we're dealing with a reactant like NO2, we're going to use that up in the reaction process. So by convention, what we do is we give that a minus, we multiply by -1, or give it a minus sign up front, okay? And the reason why that is because otherwise this would be a negative number, and I think we'll see that as we go through this problem, okay? So that's going to be our reaction rate. So if we know these numbers, we know can find them to plug in our data table, we are in business, we can solve. So let's take a look more quantitatively at predicting the reaction rate for this specific reaction over the time interval specified. It looks like the problem wants us to specify a 10 to 20 second time interval, so not the initial time period, but the rate over this interval, okay? And it looks to me like our final concentration of the NO2, which is what we're going to use to track this change, was 0.904 moles per liter. The initial concentration was 0.951. Okay, so now you sort of see what I mean by that statement that by convention we make the negative sign out here. Because if I take this difference, I'll get a negative number, since the initial concentration is going to always be greater than the final concentration if I am tracking a reactant that's used up as a result of the chemical process, okay? It doesn't necessarily always make sense to express a negative average rate of reaction, so we usually multiply that change by -1. Now, by the same token, we need to assess our delta T here. That's going to be 10 seconds. My units up top in the numerator are going to end up being changing concentration units, which are going to carry mole per liter units. And down here in the bottom, I'm going to have second units for my delta T. All right, so it's really as simple as that. I mean, that's basically what we need to do to compute our average rate over this time period. And if we do that for this particular set of data, we get 0.00407 molar per second. That's my average rate over that 10 to 20 second period. If I want to think about sig figs, I generate this delta t is usually kind of considered to be an exact interval, okay, of 10 seconds. So I basically would link back to how many sig figs I've got in my concentration term. If I want to think about sig figs, and that's going to be 3, so it looks like I'm okay with what I reported here, okay? So that would be my average rate over that 10 to 20 second interval. Now, the problem also asked me to do the exact same calculation for the 50 to 60 second interval. This is more or less the same problem, just using different data, right? Because I'm on a different period of time. So for 10 to 20 seconds, it was 0.00407. I'm just running that over here so I can keep track of it. I'm going to erase this now. This is essentially the exact same type of problem. Change in concentration over change in time. The second time interval is still 10 seconds, so that hadn't changed at all. But what will change, my numbers up here in the numerator, okay, because I've got different concentrations. Now I want this time period 50 to 60 seconds. Looks like my concentrations were 0.740 at the final condition after a minute of reaction. My initial was 778 moles per liter. Both of those, again, moles per liter unit, okay? So I take the difference and I solve for what the average reaction rate, by subtraction divided by 10, over this interval, and I get 0.0038 molar per second. Okay, going back to the 3 sig figs again, right, 380. Okay, so that's my reaction rate over this 50 to 60 second interval. So the 10 to 20 second, the reaction rate was 0.00407 molar per second, and now it's 0.00380 molar per second. So you can see that over the latter time interval, the 50 to 60 second, the reaction rate was actually a bit lower than it was earlier in the experiment, okay? And this is actually pretty darn typical, as it turns out. For most reactions, the reaction rate of decomposition, say unimolecular decomposition, for most reactions, that rate is going to be directly proportional to the concentration of the reacting species. And we'll see this over and over again in this chapter. So it's not a big surprise that the reaction rate has slowed at a latter time when some of the reactants already been decomposed and the concentration has decreased, okay? But nonetheless, this basically effectively describes the rate of decomposition over these average time periods. It would also describe the rate of this reaction. Sometimes when you're describing the rates of reaction or the rate of decomposition of certain materials or the rate of formation of certain materials, you have to be a little bit careful what the question's asking for, okay? Because here it's asking for the average reaction rate. You see these stoichiometric coefficients like the unwritten 1, the unwritten 1, and then the half over here. Sometimes obviously that can be 2 or 3 or 4. Basically what that means then is that the concentration change of all reactants and products is not going to be the same. I mean, that the rate of decomposition or the rate of formation of reactants and products is not going to be the same. It's dependent upon what those numbers are, okay? And we'll see that actually in part B of this problem, which is what I sort of want to get into now. So you have to pay attention to the stoichiometric coefficients. In part B, we're asked, what is the rate of formation of specifically oxygen between 50 and 60 seconds? Now, this is not the reaction rate. This is the rate of formation of oxygen. Right, now, the reaction rate basically normalizes out the concentration change per unit time per 1 unit of stoichiometry, if you want to think of it that way. Now, in this problem, we're fortunate because there's an unwritten 1 here for the NO2. So if we solve for the average rate of decomposition of NO2, that's going to be the same as our reaction rate by virtue of the 1, okay? But the reaction rate is always normalized out to essentially one stoichiometric unit. You divide by whatever number is out in front of the concentration that you're tracking. Now, in this particular case, for problem B, we want to know just what is the rate of formation of O2 between 50 and 60 seconds. Now, we know the reaction rate between 50 and 60 seconds is this, because we solve for it. But what does that tell us? Well, that's the rate at which this material decomposes. And that's our data plot. If we look over here, we're describing the concentration or the molarity of the NO2 over time, and we computed the rate of change of that concentration. Okay, that's our reaction rate. But does that tell us the rate at which this is formed? And I would argue that it doesn't. And the reason why goes back to the stoichiometry. For every 1 mole of this that decomposes, we only produce half a mole of our oxygen. So it appears to me as if this material, the oxygen, is forming at 1/2 the rate that this decomposes. Okay? So if our reaction rate over the specified time period is 0.00380 molar per second, okay, doesn't it make sense that we need to multiply that value by 1/2? Because this only forms at half the rate that decomposes by virtue of the stoichiometry. So in this particular example problem, that would mean that our oxygen forms at a rate of 1.9 millimolar per second, or 0.0019 molar per second. So it's pretty straightforward, hopefully. Hopefully you can all see that, okay? These are easier type examples from this chapter on kinetics. One more thing just to point out, if this wasn't obvious, notice that I wrote the units in 2 different ways for my reaction rate. They're still the same units, though. This is molar per second, or moles per liter per second. The concentration change in molarity units per second is the way I'd read that. Seconds in the denominator. And if you're not familiar with this way to write the same thing, I just wanted to point out that it's exactly the same. It's molar per second. Where I wrote my s to the -1, that's just meaning it's appearing in the denominator. It's the inverse seconds, okay? So it's the same exact unit. Sometimes you'll see it written either way. Just wanted to point out that that's a possibility. But this is example 1332, computation of the average rate, the average reaction rate